Hi, I already discussed minimum spanning tree by both Prim's algorithm and Kruskal algorithm. In today's lecture, I will discuss number of spanning tree possible for a single graph. I will discuss for both weighted graph and non-weighted graph. First, number of spanning tree in connected undirected graph. Weight are not assigned for the edges, or you can say it is a non-weighted graph. If G is a connected graph with V vertices, then number of edges in spanning tree are number of vertices minus 1. Circuit rank, number of edges we need to delete to form the spanning tree is called as circuit rank. Total edges available in graph are E, and in spanning tree total number of edges are number of vertices minus 1. So how many edges we need to delete? Total edges minus, in spanning tree how many edges will be? In spanning tree number of vertices minus 1 edges will be. So number of edges minus number of vertices minus 1. It will be number of edges minus number of vertices plus 1. So this many edges we need to delete to form a spanning tree, that is called as circuit rank. So number of spanning tree possible equals to available edges in graph combination number of vertices minus 1. So we need to choose number of vertices minus 1 edges from all edges. That's why EC number of vertices minus 1. And this is true for graph having no cycle. So maximum number of spanning tree possible should be less than equals to n power n minus 2. N is the number of vertices. So if graph is complete, then number of spanning tree possible equals to n power n minus 2. In other graph, it will be less than n power n minus 2. Or you can say number of vertices power number of vertices minus 2. So it depends on graph whether cycles are present, whether it is complete or not. But for all type of graph, we can find number of spanning tree by one theorem, that is called as Kirchhoff's theorem. So step 1, create the adjacency matrix for a given graph. Then replace all the diagonal element with degree of node. Then replace all the non-diagonal 1 with minus 1. Then find the cofactor of any one element, and that cofactor is the number of spanning tree possible. So let's take an example. Let this is the graph. So first I'll create the adjacency matrix for this graph. So if it is adjacent, I'll write 1. If it is not adjacent, then 0. So with vertex 1, vertex 3 and vertex 4 are adjacent. So from 1 to 3 it's 1, from 1 to 4 it's 1. Then with vertex 2, vertex 3 and 4 are adjacent. So 2 to 3 1, 2 to 4 1. With vertex 3, vertex 1, vertex 2 and vertex 4 are adjacent. So in third row, first column, second column and fourth column it is 1. With vertex 4, vertex 1, 2, 3 are adjacent. So first column, second column and third column are 1. Now adjacency matrix is done. Next we'll replace the diagonal element with the degree of node. So these are the diagonal element. For 1 degrees 2, for 2 degrees 2, for 3 degrees 3, for 4 degrees 3. So we'll get this, and all the 1 will change to minus 1. So all diagonal are degree while all other 1 are minus 1. Next we will find cofactor of any one element. Let me find cofactor of 1 1, that is equals to minus 1 power 1 plus 1, it's plus 1, multiplication minus 1 1. So we'll delete first row, first column, we'll find determinant of this. Let me write 2 and minus 1 here. In left side I will write minus 1 and 3. Now we'll find the determinants of minus 1, multiplication minus 1, multiplication minus 1, it will be minus 1. Then 2 multiplied by 3, it's 18. Then minus 1 multiplied by minus 1, multiplied by minus 1, it's minus 1. So minus 1 plus 18 minus 1 minus, then 3 multiplication minus 1, multiplication minus 1, it's 3. Next minus 1 multiplied 3 multiplied minus 1, it's 3. Then minus 1 multiplied minus 1, multiplication 2, it's 2. 18 minus 2 is 16 minus 8 will get 8. Number of spanning tree possible are 8. So this is all about non-weighted graph. If weights are assigned, then how will find the number of minimum spanning tree? If all weights are distinct, then just one minimum spanning tree possible. If equal weights are available, if more than one weights are equal, and there are cycle present, so based on this cycle and how many equal weights are available, multiple spanning tree possible. So it's depend on graph. Suppose this is a graph and here weight 2, here weight 2, here weight 1. So now in spanning tree we'll choose weight 1, then from these two to any 1, 2. So there are two spanning tree possible. One by choosing these two, another by choosing these two. So based on how many cycles and how many weights are present on that cycle, multiple spanning tree possible. And if all weights are distinct by both Prim's and Kruskal's algorithm, we'll get single minimum spanning tree. If all weights are not distinct, means equal weights are available, then there may be different minimum spanning tree, but total weight will be same. Let's solve one problem. Consider a graph whose vertices are present in a plane with integer coordinate x, y, 1 less than equals to x less than equals to n, 1 less than equals to y less than equals to n. N value should be greater than 2. x1, y1 and x2, y2 are adjacent if and only if x1 minus x2 less than equals to 1, y1 minus y2 less than equals to 1. The cost of such an edge is distance between them. Compute the weight of minimum cost spanning tree of such a graph for a value of n. N value greater than 2. So let me take an example for n equals to 3. First I'll write the coordinates. So 1, 1, 2, 1, 3, 1. Then 1, 2, 2, 2, 3, 2, 1, 3, 2, 3, 3, 3. So these are the vertices. Next I'll check which vertices are adjacent. So two vertices will be adjacent if x1 minus x2 less than equals to 1 and y1 minus y2 less than equals to 1. Let's check these two. So 2 minus 1 it's 1, 1 minus 1 it's 0. So both are less than equals to 1, that's why they are adjacent. Then 2, 1, 3, 1 adjacent, 3 minus 2 is 1. Next 1, 1, 1, 2 are adjacent, 2 minus 1 is 1, 1 minus 1 is 0. Both are less than 1, they are adjacent. So like this, let's draw all the adjacent. Next we'll find the weights. So weight is the distance between them, and for distance formula is x1 minus x2 whole square plus y1 minus y2 whole square root over. Let's find distance between these two nodes. So 2 minus 1 whole square plus 1 minus 1 whole square whole root over. 2 minus 1 is 1 square, it's 1. 1 minus 1 is 0, 0 square is 0. So 1 root over, it's 1. So here weight will be 1. So like this we'll add 1 for these edges. Next we'll find weight for the cross edges. Now 1, 1, 2, 2, 2 minus 1 whole square plus 2 minus 1 whole square whole root over. 2 minus 1 is 1 square, 1 plus 2 minus 1 is 1 square, so it's 1. 1 plus 1, 2 whole root over. So here weight will be 2. For all the diagonal edges, weight will be root 2. Next we'll find minimum spanning tree. So first I'm writing all the nodes, and from 1 and root 2, 1 is lowest. So first we'll choose 1. So this is one spanning tree. We can also draw like this. There can be different minimum spanning tree. So in this graph, number of vertices equals to 9. So number of edges in minimum spanning tree will be 8. We'll choose 8, 1. Now cost of this minimum spanning tree is 8. So when n equals to 3, cost of minimum spanning tree is 8. When n will be 4, in the graph there will be 16 vertices. So for 16 vertices, there will be 15 edges, 15, 1. So cost of the spanning tree will be 15. For n equals to 5, number of vertices will be 5 square, that is 25, and number of edges will be 24. So from these you can get a pattern that for n vertices, cost of minimum spanning tree will be n square minus 1. In today's lecture, I discussed how to find number of spanning tree for a single graph, for weighted graph and for non-weighted graph. In case of weighted graph, if all weights are distinct, there will be one minimum spanning tree. If all weights are not distinct, then there can be multiple spanning tree possible based on number of cycle and equal weights. And in case of non-weighted graph, by Kirchhoff's algorithm, we can find number of spanning tree possible for that graph. If today's lecture is helpful for you, please like, subscribe and share. Thank you.